So today I will talk about the trustworthy and applications on autonomous vehicles. So I want to thank my students and my collaborators. So without them, I cannot achieve any of this achievement. Okay, so autonomous vehicle or autonomous robot has been prevalently deployed in the recent years thanks to the advances of artificial intelligence in general. And in my opinion, there are three biggest threats that have changed the way we make machines. The first one is I use three journal articles from the Science journal. So the first one is we have this deep learning, right? Deep neural network, and that is in contrast of traditional way procedure, like the way we design machines with the way procedure. So we give up of the concept of subsystems and we fully embrace the connectivity. The second one is reinforcement learning. So here we can see that we have a evolving system that is in contrast with the traditional waterfall model. It is called waterfall model because once you go down, you will not come back. But for reinforcement learning, so it actually has its own dynamic of evolving. So this is another change. The third one is we are in the age of information explosion. So traditionally, we have closed source, and also we do not usually share data. But now the trend is that usually people share their work with open source with both code and data. So these three changes actually enable the change of the way we make machines. Here I create an interesting slide today. That is a comparison between human and artificial intelligence. So we know that 仁义礼智信, right? So that, but you probably do not know that when Confucius first mentioned about these principles, he only referred to 仁义礼. Well, after that, Mengzi actually added 智 after 200 years ago. And then finally, when in the Han Dynasty, so when system is so complex, and we Dong Zhongshu add another term, another principle called Xin. So I think this is actually very similar to it's a great energy to how we developed artificial intelligence in general in the last century. So in the last century, the first I would say 50 years, people spent a lot of effort in defining ethics and solving real problem, which represent 仁 and 义, and also standardize the terminologies, which corresponding to Li. And then after in the last 10 years, we start to work on more complex problems that is with the development of deep learning. So this corresponds to 智. And in the last 3 years, people start to work on 信. In my opinion, this is very similar to what we are talking about as a trustworthy AI. So a more formal definition of trustworthy AI can come from the European Union. So they in their report, AI, this HLEG, so they defined the artificial intelligence, trustworthy artificial intelligence. They say the trustworthy should not be interpreted here in its literal sense, but rather as a comprehensive framework that includes multiple principles. But in general, it wants to maximize the benefits of AI systems while at the same time preventing and minimizing their risks. So just a few months ago, the European Union published the report called Trustworthy Autonomous Vehicles. In this 70 or 80 pages report, they defined what is a trustworthy autonomous vehicle from several aspects. And not only the government, but also almost everyone in the industry and in this field start to care about trustworthy AI. So for example, Google, they start to care about trust. For example, Google, IBM, Microsoft, OpenAI. So those companies have their own department or their research group working on trustworthy AI. Well, National Science Foundation of the US also launched 2 centers on trustworthy AI, and Stanford, Princeton, Stanford, Pennsylvania, University of Pennsylvania also have their own center for safe AI or AI safety center. So also some NGO also focus on the trustworthiness of AI. So in my lab, we also our lab is called a Safe AI Lab. So at CMU, we want to study trustworthy AI and apply them mainly into applications. So one is mobility, another one is healthcare. We believe these 2 are very important fields. So you need really a trustworthy artificial intelligence to fully deploy those technologies. So in other words, we require them not only intelligently autonomous, but also trustworthy. So our mission is to develop trustworthy AI by bridging rigorous theories and practical technologies. You can see this theme actually goes through all my talk, that we want to dive very deep into the theory, but also we want to bring our new theories and use them really to solve the real world problem. So in today's talk, my work mainly focus on the following area. So here I use 3 circles to represent the 4 terrain. So the blue one represents how we model the environment. The red one represents how we design the agent, the autonomy, and the yellow one represents how we can evaluate our preference. The preference will ultimately come from human. So when we modify the environment, when we encounter new environment, the problem is actually can dive into the generalization issue. And the algorithms usually need to care about the robustness. And the combination of these 2, well, we view that the safety play a very important role once you know your environment and you know your agent. And also we want to evaluate across a different field and also the robustness against the noise. So we want to do the certification. So today's talk will mainly focus on those keywords in the red box. And particularly, I want to cover 3 topics. The first one is safety critical digital twin generation. Second one is robust, safe, and generalizable reinforcement learning. And the third one is I'll briefly mention about the third topic, that is evaluation and certification for intelligent autonomy. I want to say that the terrain of trustworthy AI is very broad. And here, for example, here in the human centricity topic, we have explainability or privacy or other topics such as fairness. So I will not cover. I think they are very important topics, but I will not cover them in today's topic. All the papers I mentioned in today's talk can be downloaded and found from this website. And also I summarize them into 3 categories on the front page of my lab's website. Okay, you can also stop me if you have questions. Okay, so here I say I view these 3 key features as the intrinsic of trustworthy AI, and also the evaluation certification are the critical bridge that between the intrinsic and extrinsic, which represent the human preference. Okay, so let's start with our first topic, safety critical digital twin generation. So you see we have here in our recent survey paper, we go through all the existing driving database data sets and also simulators. You can see people have spent already a great effort in studying how to generate driving scenarios and also simulate the driving scenarios. However, we believe there is a big gap between the way we collect the data and the approach that we use to generate the critical scenarios, particularly the consequential safety critical scenarios. You can just look at this figure. That is that's a histogram recorded by California Department of Motor Vehicle Disengagement. Here, the higher the bar usually shows the car needs fewer disengagement. From one thing, it may shows that the car is safer, but however, from another perspective is that the safety critical scenario collected from this company is actually pretty sparse. In other words, the safer the car, actually, the more likely that we can collect interesting scenarios such that we can use them to test and improve our vehicle. So this can be a really paradox. So that the majority data we collect from the real world is actually safe, while the most important parts that we can use for safety critical scenario generation is actually pretty sparse. So how we could maximally utilize the data we collected to create the safety critical scenarios is actually an ultimate challenge for safety critical scenario generation. It is a challenge because from one side, it's very hard to collect the really safety critical scenario from the real world. On the other hand, it's actually the scenario we generated from fully virtual scenario. It actually could be non-realistic and also lack of diversity. So the key questions we want to ask today in today's talk is how we can define the safety critical scenarios and why are they rare, how to evaluate the gap and how large is the gap between these human driver scenarios and autonomous vehicle scenarios, and third, how we can generalize them. So I will mainly introduce 3 different approaches. The first one is called a data-driven scenario. Second is adversarial scenario generation. And the third one is knowledge-based scenario generation. So let's dive into the first one. For data-based scenario generation, you can see it's pretty straightforward. So you have we collect some data. It's usually very high dimensional, either in sequential, in temporal dimension, or in spatial dimension. So we need some like feature extraction method. And after that, we could have a distribution of the latent code. And when we sample the latent code, we sample the learned latent space, we can sample the trajectories that come out of the encoder, the decoder. So this is basically the pipeline for database scenario generation. So we actually implement that a few years ago, 3 years ago, and we are one of the first team to use the data to generate the driving scenarios for encounters of autonomous vehicles. However, this method has some issue. Oops. This method has some issue because the latent space is actually a virtual space, so it may not have any meaning. And also, more importantly, this may not create the safety critical scenarios we need because it just represents the real data, right? So when we sample, we still sample in the latent space with some distribution. So then we come up with an interesting idea. Another issue is that may now be able to generate more complex scenario that considering the road shape or other things that is released in the real world. So an interesting method we created is that using conditional variational autoencoder is that, so we are using 2 databases. One is we call safe database. That is the data we collected from the real world. Another one is we just using a collision database. The collision database can come from GDAS, or in China, we have the CDAS. So we by combining these two databases, so we can generate a mixed latent code that that can actually have a parameter such that we can tune the severity of them by saying, so how likely we want that to be safe or unsafe. We also we also have this conditional version autoencoder on the road. So you can see here, this two instances are coming from different road shape. A naive combine of them may actually have a very bad consequence, because they have distinct distinct road shape. So, but if we conditional on the road shape, then we can actually generate some scenarios that are in some road shape conditional on this road, right? And also we have the generalized data that can represent different level of severity. In this case, we are using a linear combination between the safe data set and unsafe data set, right? So we combine these two, and we using this lambda to tune how likely we want the scenario to be risky, how risky the scenario we want them to be. Right. So here another issue is that, okay, so this may apply for two-dimensional scenario. How about we want a very complex scenarios that cannot be easily learned by a single model? So the one way is that we could use a hierarchical learning model. So this is another work we have done using unsupervised learning, particularly Bayesian non-parametric. So traditionally, the scenarios are defined by human. Then we cluster the data and put the data into one bin and do the modeling using VAE or other method. But this is quite subjective when we define what the types of scenarios. So here we call it traffic primitive, because we are extracting the fundamental building blocks for driving data and do a automatically infinite dimensional clustering, such that we can extract the key different component in the driving. So I'll give one example to illustrate the idea. So here is a map that the white dots represent, each dot representing an encounter between two vehicles. And here, after we do this clustering, Bayesian non-parametric clustering, so you can see different color represent different type of encounters. Well, in the highway, usually that's one color because that's just one car follow another. Well, here in the intersection, you see that it's more colorful represented in the intersection is actually much more complex. So eventually we can clustering all the encounters into this 20 clusters. And by the way, this 20 cluster is a sample itself. The number of cluster itself is a random variable, so that we can, the more data we have, we'll automatically learn more type of these scenarios. So this is like a Bayesian non-parametric learning way to extract the scenarios. A further more crazy idea is that we found some YouTube video about this very complex intersection. This is in Ethiopia, African country. So we want to ask ourselves a question is, so what if this is a given to us as a transportation engineer? This could be a nightmare for a transportation engineer to analyze, but can our method help? Right, so how we can define the scenario in this situation? So we apply similar method, but with some pre-processing method. This is a YouTube video, so we do not know the camera, so we do some approximation and do some tracking algorithm. And then after that, we use a Bayesian non-parametric to extract the key scenarios. And we found that these 6 key scenarios, that if someone want to practice driving in this situation, those are the scenarios that you may want to test yourself, whether you're ready or not. So in summary, data-based scenario generation The good thing is it use real world data, and it has some kind of controllability, right? So when we combine the collision data set with a free data set, a collision free data set, however, has poor adaptivity and no interaction with the downstream task, meaning it could be a little bit inefficient. And it only uses existing data, so you may now be able to generate more diverse safety critical scenarios, which is critical for the edge cases. So another approach is called adversarial scenario generation. That is, we want to put this the ego agent in the loop. So when we do this simulation, so this will update will update the generated model based on the behavior or performance of this autonomous vehicle agent. Right. For example, in this case, we model a cyclist that will interact the vehicle. Depending on how this vehicle will respond, the cyclist will adjust its strategy to try to cause the safety critical scenarios. So this is one example. So, however, in this case, we are not only try to attack the ego agent, which could be sometimes meaningless if we just want to simulate a cyclist that just want to suicide, right? So we also want the behavior of the cyclist that could be as realistic as possible. So we need to add this prior model that is trained from the real world data set. And also in this situation, you can see that we have different patterns that the cyclist will interact with the autonomous vehicle. So our agent, our scenario generator need also to be multi-model to capture all the scenarios. So in this case, we designed the prior model to represent the probability of scenario happening in the real world. We'll also use a normalizing flow model to estimate the multi-model distribution and design a multi-model adaptive learning mechanism. In this case, we can generate these driving scenarios for autonomous vehicle that is trained by 6 different reinforcement learning algorithms. And interestingly, I think we found that those reinforcement learning, although if they are training in the normal environment, their behavior is very normal, behave very similar. And if it's trained and tested on the same normal environment, all of them behave very well with a very low collision rate. But if they are trained on a simple environment and test on the more safety critical scenario, then some will still behave very well. For example, model-based reinforcement learning, while other model-free reinforcement learning may be very sensitive they may not even learn. They probably just memorize what happened. They may not really learn how to avoid the collision. So their behavior is pretty bad. And we also found out, so if we train on the hard safety critical scenario and test on the normal database, then all of them behave very well. Because if you can pass the hard test, we assume you can also pass the simple task. And finally, if we train on the hard and test on the hard, some of them will still behave very well, again, like model-based. Well, the other part, they may not be able to learn the safety critical scenarios, and the behavior of them could be quite different. So in this case, although the normal reinforcement learning training will only care about this situation, that they just follow some distribution and they test on the same distribution. In our case, once we generate the safety critical scenario, we can actually weigh the different behaviors for the different reinforcement algorithms. So in summary, so the adversarial scenario generation is very adaptive and can interact with the downstream vehicle, downstream task, and it consider real world data, and also it can deal with diversity. However, it still probably have a poor generation if the scenario is very different. So And also sometimes we can generate some scenario that will force the autonomous vehicle to violate the traffic rule. In this cases, and if we have extremely less data, so we want to incorporate some knowledge in the generative model. The knowledge can be just given like a traffic law, or the knowledge can come from the real world. We learn from this data set, and we can use like a knowledge distillation to learn the knowledge and then apply this knowledge in the generative model case. The knowledge is very important. For example, this is a LiDAR point cloud that you can see if a tree, if a car that is in front of a tree, usually the LiDAR may actually ignore this car, as you know, usually we now expect that the car will be beside the tree or on the tree. Or when this car is enter a garage, usually this car is missing because usually this is not commonly seen from the real world. So in these cases, we do not want to generate such a scenario that is a tree on a car or the car is in the wall, right? So yeah, so this is important to impose some physical law to avoid this kind of scenario happening. So how to do that? Remember, this is a recap of the first method with the data-based scenario generation method. We have this latent code. So from this latent code, we can use some structured encoder and decoder such that we can interpret this latent code and pass some knowledge based constraint into the latent code. So in this case, if we know the knowledge tells us that not all the latent codes are feasible, only the one that in this circle is actually follow the physical law. So if we are sampling, we are using sampling method to find the Adversarial scenarios, then we can use a projection method to project those points back into this domain, such that all the scenarios we generate are follow the traffic rule or follow some physical laws. So the way we use to encode this knowledge is we use a tree structure. We use tree structure because it's interpretable, and we can incorporate those knowledge into this tree structure. Right. So particularly, we are using this method can be used to deal with high dimensional data. So in this case, for example, we want to attack the LiDAR point cloud by generating some scenarios to attack the LiDAR point cloud algorithms for autonomous vehicle. The normal approach is used to just perturb the point. We call it a point attack. It's actually not very efficient algorithm. The second one is we call the pose attack. That is, we can rotate the car. It is effective, but it's actually not realistic because you may now see many cars that driving the vertical position. The third one is what we call the scene attack, that we learn the natural distribution of the position of the car, and then we can search in this space by imposing some simple laws that, for example, car will be on the road, car cannot collide with each other, or car you should normally keep a distance from each other, so that we can quickly search some common scenarios for this scenario, for this case. And we use that to attack 4 very popular point cloud algorithms, including point9++ and Cylinder 3D. So we found out that those scenarios, we can efficiently attack those scenarios with our method, while those pose attack and point cut are not as effective as we are. So yeah, so that's the first topic about safety critical digital twin generation. Particularly, I mentioned about safety critical scenario generation. And if we cascade, our next step is we want to cascade many steps together to generate a more complex scene, which eventually converge to a digital twin of the real world, a complex real world. Okay. So the second topic I want to mention is this: how we can design robust, safe, and generalizable reinforcement learning algorithm. we say deploy AI to the real world is hard. Many people has start to thought about this, start to think about this, but it's actually pretty difficult. One reason, we see a lot of papers on using Atari game and Dota and simulator and also AlphaGo, but fewer experiment is on the real world robotics or self-driving car using, for example, reinforcement learning to train it. And one reason is because this match between the simulator and also the simulator and the real world. Another one is usually people have some safety concern when deploy reinforcement learning into the real world. So we study a few series of topics. So the first topic we study is that we want to study how a particular factor will influence the deployment of reinforcement learning in the real world, which is the delay. Delay is very prevalent in the real world from robotics, autonomous vehicle, hydraulic system. So we found out this delay. For example, we have this some delay happening in the array steps in the system, and it's usually not ignorable. So right. So how to deal with that? So one method we propose called delay-aware model-based reinforcement learning is that we will incorporate the delay and state and action into the state. So in other words, we augment the state so that we can consider the delay. So that's our first work. We found out that actually delay is actually quite most of the existing reinforcement algorithm is quite sensitive to the delay, even if the delay is just one step delay, which is pretty small in a traditional perspective. However, you can see many algorithms start to have very big decay when the delay is just one step. In this case, the blue curve is the reinforcement without delay, which can work as the upper bound of our algorithm. Well, our algorithm is this red curve. You can see even with some delay, we can almost approximate the upper bound. Well, other algorithms in this, we use Atari game to, we use a Madrigal environment to test it. Other algorithms can fail very badly, even with the one-step delay. We also tested that what if we have a longer delay, not only one, but a 2, 4, or 8 step delay. In this case, the performance can decay. The performance can decay very fast. So for this our reference, a SOTA method called RTAC. This is a method is particularly designed to deal with the delay, but our method is actually can perform very well even with very different types of delay. Okay, so that's the first work we deal with the delay. Here, actually, we make a very big assumption that is, we assume we know we have very good guess of the delay duration. But what if we do not have this information? So then one method we're thinking about is using the so-called robust adversarial reinforcement learning. Recall in the scenario generation part, we are generating the adversarial environment. Here we are using the similar idea to train a reinforcement learning agent. So the idea is that we are designing the adversarial world and use that to train the reinforcement learning agent. And once this agent is trained in this very adversarial world and deploy this one to the real world, we hope this agent can deal with some very bad situation. So there are some limitations of the existing method in this direction. The first one is, the existing work usually assume there's a zero-sum setting in the adversarial situation. Well, this will usually encourage the adversarial to generate some extremely difficult or even unsolvable environment, which can make the agent overly conservative and may not even to be able to learn. So in other words, suppose if a professor gave you some really hard exam, then you probably will give up for that course. So this is kind of the situation in the RL. Another one is the training is using a gradient ascent method. While each agent naively take the partial derivative of its objective with respect to its parameter, so it may result in unstable training. So we are using a Stackelberg dynamic to replace the Nash equilibrium. So in this case, we hope this training can be more stable. So and also we use a regularized adversarial to try to make the environment less aggressive adversarial, so it may not generate the unsolvable environment. So apply this work to autonomous vehicle driving. In this case, if you only apply this RAL method, then what happens is the adversarial will generate a very, very severe situation. So if you're using that to train your autonomous vehicle, then you may lead to a very conservative policy. So basically the car dare not to move at all. So use our robust like regularized learning method with Stackelberg learning. We found out our training is much more smoother and the performance is better. So in this figure, we see that even though the opponent has a larger and larger aggressiveness, the performance of our algorithm should be quite consistent, while the one without the adversarial training will decay very fast, and the one with the robust adversarial reinforcement learning will be very bad at the beginning. It will be bad even though the opponent is not that severe. So the performance is much lower than ours, because it actually does not learn at all from this training curve. So yeah, so we also, by the way, in this paper, we also studied the delay method, and we see the same situation. Okay, so in this case, we can deal with a environment that we have some unknown parameter, but this unknown parameter, even is unknown, is actually fixed. In other words, it's a stationary environment. What if we encounter an environment that is changing all the time? It's non-stationary. So for example, in this situation, so we are feeding the patient with this robotic arm. This is different from the traditional environment, is that this patient has, maybe it's just a senior people, so it's a senior person, so it has some shaking of his head. And the way the patient shaking his head is changing most of the time. Sometimes it's shaking hand in this way, sometimes shaking hand this way. So it has 4 degrees of freedom of changing. So we need to train a robust reinforcement learning to deal with this non-stationary environment. In this case, we introduce the contextual aware safe reinforcement learning by using the observation as the context, and use that to drive this Gaussian process model, so that we can learn the context and use this context to guide the training of the reinforcement learning. In this case, we can have a very efficient and robust stable algorithm to deal with the non-stationary environment. Okay. However, then we also ask another question: what if these contexts are very, very different from each other? In other words, we are probably dealing with more like a meta-learning situation. So that but we do not have enough data, so we still want to learn from different data sets. Remember what we did in our previous one, right? So when we use the data-driven method, we actually invented this this approach using the Bayesian unsupervised Bayesian non-parametric to first cluster the scenarios. So we actually did the same thing when we incorporate this into the reinforcement learning domain. That we design this task agnostic hierarchical reinforcement learning such that we use the data buffer to train a mixed infinite dimension of mixed model that is represented by Gaussian processes. And with this one, we can use that as the model-based reinforcement learning and quickly switch between different models if we are encounter a very different scenario. For example, we apply this to some half-cheetah that, for example, some part of the half-cheetah broke, or we are using that to deal with this intersection scenario that you may have very distinct driver that will drive in different strategy. So in this case, a model it as a non-stationary environment is not enough. We actually need to have a concept of a hierarchical concept of scenarios to deal with this situation and make it to be an efficient learning algorithm. So yeah, so far so good. We seems we can deal with a very complex scenario already. But what if the learning procedure or the environment has some safety concern, have some safety critical applications? So we have this another dimension we are considering. So for example, this is some funny videos I found from YouTube, and you can see when we train the robot, it actually can do some really stupid tasks. So how we can constrain the reinforcement learning and deployment in both learning and deployment procedure. So we published one first paper using some cross entropy method using a policy revolutionary method. Then we also apply this to people in this field, in the safety field, actually created this common environment called OpenAI Safety Gym. In this situation, that they have various of tasks to check the awareness of safety and how they can deal with the safety based reinforcement training. So you can see here the major benchmark is the Lagrangian based method using a dual primal dual form. However, we found this primal dual form has some really fundamental problems. That is lack of optimality. The training can be very unstable. You may not have guarantee of convergency. Well, in our recent paper, we propose a new structure for safe reinforcement learning, such that we can decompose this procedure into two steps: the E step and M step. M step we make it to be a supervised learning, and the E step through a versional inference. So we can make this, we can prove and make this E step to be a fully convex optimization. In this case, we not only can prove this is a very optimal strategy for general constrained Markov decision process, and also we could prove the robustness of this method thanks to the convexity of the way we solve the problem. So we actually achieve several order of magnitude of advances compared to the common scenarios. And the learning ratio between performance and the violation we need through the way is greatly improved. So finally, all of our existing methods, many of them can be extended to multiple agent situation. So we also have done some exploration. For example, these two papers in the multi-agent in this logistic robot situation, or in some multi-vehicle delay study. This is a study of the multi-vehicle with some communication delay, for example, way-to-way communication. Okay, so that's my second topic. I will very quickly introduce the third topic about evaluation and the certification for intelligent autonomy. Because all of them, after we achieve all of them, those are nice features. So we still, and we created the driving, the scenarios, we still need to combine these two together and test whether we indeed have such a feature, have achieved what we want to do. So this actually dates back to my PhD study on the accelerated evaluation of autonomous vehicle, which now has been considered as the standard way in some testing facility. For example, this is M-City at Michigan. So this is a very broad topic. I do not have time today to cover all of that. Itself, I may need to spend one talk on it. But I have a series of study on this. The key concept is called accelerated evaluation. And I'm still very active in this field and publish papers in the recent years in this area. So we want to achieve rigorous, adaptive, dynamic, accurate, robust, and to also use that to evaluate the reinforcement learning and also evaluate the high dimensional space. So there's a long series of work in this area and has been supported by many great sponsors. So I just very quickly introduce the idea of this accelerated evaluation. That is, after you have the data, you do the modeling. That is the same as the generative model we safety critical scenario generation we just mentioned. Then we want to skew the statistics with the agent in the loop. So this is similar to the adversarial data scenario generation. The key step is that after that, we want to use the importance sampling to link between the results we had in this accelerated environment back to the one that in the naturalist study. So this is actually the hard part in the evaluation. That depends on different algorithms you want to evaluate and the different models of the world. These steps may require quite different techniques. And after that, there are three three key steps you need to make the evaluation happen. Modeling the world, apply the importance sampling algorithm, and also work on some realistic platform. Either it could be simulation, it could be artificial augmented reality, or it could be the physical test. Another work I want to briefly mention is that the certification of robustness of reinforcement learning, and my collaborator, Professor Bo Li, who just gave a talk 2 weeks ago, also in this forum, this work I think is very important because this is our first work that is trying to evaluate the robustness of reinforcement learning for both the normal reinforcement learning algorithms and also the offline reinforcement algorithms. We named them as CROPA and COPA. So we also have two leaderboards such that we can compare between different reinforcement algorithms regarding their robustness in several high dimensional and low dimensional environment. So in other words, we are not only able to evaluate the performance of very complex scenarios, but also we can even provide a certification, meaning we can guarantee if the disturbance is smaller than a certain degree, the performance will be lower bounded by those certification algorithm. So in next time when you pick the algorithm, so not only I think we should consider in summary, so next time we'll pick for example, reinforcement learning algorithm, not only you may want to consider the accuracy or performance of the reinforcement learning, but also you want to study or check the robustness of this reinforcement learning against the disturbance, and also whether the reinforcement algorithm is able to maybe inject some safety awareness into its learning and deployment procedure. I think this mindset is actually very important for us when we want to develop trustworthy artificial intelligence. Okay, so I think that's all of my talk today, and I want to pause and welcome questions.